did that just go? All right, so we are moving on to the Big Bang Theory. Okay, so here's basically the timeline of the Big Bang from the Big Bang to present day. All right, when you think about time, right? Neil deGrasse Tyson actually had an entire series about time and all about science in general. But one thing that really struck home to me was if you were to take a calendar year from January 1st to December 31st, okay, and say that was the start from, if January 1st is when the Big Bangs happened, we wouldn't show up in time until December 31st around 11:59 p.m. So that's how small and insignificant amount of time that we've been around. So the entire calendar year basically has happened. We didn't show up until about 11:59 p.m. on December 31st. Okay? So just to put that into perspective. So what happened during the Big Bang?
I think everyone wants to know where we came from and how the universe began. Cosmos can help us find answers to those questions. Hopefully, when we understand how the universe began, it will give us a clue as to why it began the way it did, or even why it began at all.
All right. So, all right. So, what did the Big Bang sound like in general? Right. So the Big Bang sounded more like a hum. Right. You don't have to write any of this down. All right. But you hear that background noise that's happening right now? That's what they assume that the Big Bang actually sounded like. Okay. Kind of, to me, it kind of sounds like a plane that's landing. So this is what they think the Big Bang actually sounded like. Okay. It happened about 13.7 billion years ago. All right. We say 13.7 because it's approximately the average between 12 and 15 billion. Okay. Remember, you have to know these times. You have to know that the Big Bang is about 12 to 15 billion years ago. Okay. You have to know when our solar system started. Right. Okay. So the sound you just heard was created by physicist John Kramer. You don't really need to know him um, that much, but it's just kind of interesting. That sound is what they assume happened when the Big Bang happened. Okay. So the whole thing is that we started off as a single point. Right? That single point was extremely dense. It became unstable and exploded, kind of like when we saw the video of fusion happening, right? You had these nuclei that were very unstable, and then boom, we had this big bang that happened. That's pretty much what is saying that it started off with. All right. Something that's very important is that today the universe is ever expanding. It's still expanding. It's not just staying as close together as it was originally. They are continuously moving out, and we're going to prove how we know this is happening. Right? So, what's important about this slide? Number one, how long ago did the Big Bang happen? So it happened between 12 to 15 billion years ago. The most common date that people talk about is 13.7, okay, billion years ago. That originally all matter started off as a single point, all right? That point was very unstable and it exploded outward, all right? And according to Hubble's law, the universe itself is moving further and further and further and further and further away from each other. When we talked about the moon and eclipses, remember in the video, the narrator said at some point the moon is going to be so far away from us that it won't be able to cover the sun from our perspective, or we won't be able to cover the moon from the sunlight. So eclipses will not happen anymore. It's because everything is moving away from each other. Okay. So, what is the Big Bang Theory in general? Like we said, the universe started as a single point. Here's just a review. That point was extremely dense. It became unstable and exploded outward. Okay? Right? And today the universe continues to expand. Very simple, very easy. So let's talk about the universe. All right? So the universe began with that massive explosion that occurred between 12 and 15 billion years ago, and we have been ever expanding ever since. So this is already something you wrote down. You don't have to worry about writing it again. This picture here, all right, basically shows you where everything is. If you would like, you can take a picture of it. Okay, so we started off with the Big Bang at time 0, which should make sense because it's the beginning of all time. Then inflation is going to happen. This number here, 10 to the negative 32 seconds. What that means is that if you were to take a number, it's 0.000000000 31 zeros with a 1 at the end. Okay, this is what's known as scientific notation. You can take very large or very small numbers and convert them into easier things here. So instead of writing out 31 zeros, right, you can instead write 10 to the negative 32, and scientists understand what's going to happen. Okay, so our modern universe doesn't happen until 13.7 billion years later. Okay, so looking at this is basically how it was formed, right? Again, here's another picture that basically says the same thing, but with a little more details. All right, we started with the Big Bang. We got quantum gravity. It turns into all this other stuff that you don't need to really know the difference for Regents Earth science. Okay, but look at it. It happened in a matter of seconds. Right? It hasn't even reached 1 second yet, right? At this point, it's still under a second. Right about here, we're at 10 seconds into it, okay? So on and so forth. And then eventually, we're about 15 billion years. Okay, so we're going to watch a little video clip that explains this a little bit better with video.
What if I told you there was a secret place where all of your favorite YouTubers hung out and put up special ad-free video?
Nope.
The beginning of everything, the Big Bang. The idea that the universe was suddenly born and is not infinite. Up to the middle of the 20th century, most scientists thought of the universe as infinite and ageless. Until Einstein's theory of relativity gave us a better understanding of gravity, and Edwin Hubble discovered that galaxies are moving apart from one another in a way that fits previous predictions. In 1964, by accident, cosmic background radiation was discovered, a relic of the early universe, which together with other observational evidence made the Big Bang the accepted theory in science. Since then, improved technology like the Hubble telescope has given us a pretty good picture of the Big Bang and the structure of the cosmos. Recent observations even seem to suggest that the expansion of the universe is accelerating. But how did this Big Bang work? How can something come from nothing? Let's explore what we know. We can ignore the beginning part for now. First of all, the Big Bang was not an explosion. It was all space, stretching everywhere, all at once. The universe started very, very, very small and quickly expanded to the size of a football. The universe didn't expand into anything. Space was just expanding into itself. The universe cannot expand into anything because the universe has no borders. There is, by definition, no outside the universe. The universe is all there is. In this hot, dense environment, energy manifested itself in particles that existed only for the tiniest glimpses of time. From gluons, pairs of quarks were created, which destroyed one another, perhaps after giving off more gluons. These found other short-lived quarks to interact with, forming new quark pairs and gluons again. Matter and energy were not just theoretically equivalent, it was so hot they were practically the same stuff. Somewhere around this time, matter won over antimatter. Today, we're left with almost all matter and nearly no antimatter at all. Somehow, 1,000,000,001 matter particles were formed for every 1,000,000,000 particles of antimatter. Instead of one massive ultimate force in the universe, there were now several refined versions of it acting under different rules. By now, the universe has stretched to 1 billion kilometers in diameter, which leads to a decrease in temperature. The cycle of quarks being born and converted back to energy suddenly stops. From now on, we work with what we have. Quarks begin forming new particles, hadrons, like protons and neutrons. There are many, many combinations of quarks that can form all sorts of hadrons, but only very few are reasonably stable for any length of time. Please take a moment to appreciate that by now, only 1 second has passed since the beginning of everything. The universe, which has grown to 100 billion kilometers, is now cold enough to allow most of the neutrons to decay into protons and form the first atom, hydrogen. Imagine the universe at this point as an extremely hot soup, 10 billion degrees Celsius, filled with countless particles and energy. Over the next few minutes, things cooled and settled down very fast. Atoms formed out of hadrons and electrons, making for a stable and electrically neutral environment. Some call this period the Dark Age because there were no stars and the hydrogen gas didn't allow visible light to move around. But what's the meaning of visible light anyway, when there's nothing alive yet that could have eyes? When the hydrogen gas clumped together after millions of years and gravity put it under great pressure, stars and galaxies began to form. Their radiation dissolved the stable hydrogen gas into a plasma that still permeates the universe today and allows visible light to pass. Finally, there was light. Okay, but what about the part we didn't talk about? What happened right at the beginning? This part can be defined as the Big Bang. We don't know at all what happened here. At this point, our tools break down. Natural laws stop making sense. Time itself becomes wibbly-wobbly. To understand what happened here, we need a theory that unifies Einstein's relativity and quantum mechanics, something countless scientists are working on right now. But this leaves us with lots of unanswered questions. Were there universes before our own? Is this the first and only universe? What started the Big Bang, or did it just occur naturally based on laws we don't understand yet? We don't know, and maybe we never will. But what we do know is that the universe as we know it started here and gave birth to particles, galaxies, stars, the Earth, and you. Since we ourselves are made of dead stars, we are not separate from the universe. We are part of it. You could even say that we are the universe's way of experiencing itself. So let's keep on experiencing it until there are no more questions to ask.
Yay. So I don't know if you guys really caught that. At the very end, he's talking about how we are basically made up of stars. What happened was, and it's funny because I read this book to my kids all the time, is there's all these books that you can, it's basically science for toddlers. And one of them is how to become a quantum physicist. Now, it sounds way over your head, but it's really not. If you remind me, I will actually show you guys it on Wednesday. It explains how, because of the start of the universe, we actually, as the hydrogen is turned into helium and things are pulled out and stars die and the elements are left over, eventually it trickles down into Earth and help to create the Earth that we know as, that is, what we know. Basically, because we live on Earth, some of those elements that help to create the Earth also help to create you, which is honestly very cool if you think about it, because as the stars died and gave off these elements, some of those elements are now inside of you. So technically you are a star, or technically, if you want to really categorize it that way, part of you is a star. I don't know. Personally, I think that's pretty cool. All right, so like everything else, everyone's like, oh, well, how do we know that the Big Bang happened? Well, here we have evidence, okay? The evidence is what's known as the Doppler effect and that cosmic background radiation. That cosmic background radiation I showed you guys in the video where we were the speck of dirt on the bum of the ant, right? And we pulled back out into the universe until we get as far away. And I said to you, that's cosmic background radiation. That cosmic background radiation shows us that the Big Bang actually happened. Okay. If you guys are following along, we're on review book page 39. Okay. The second thing is known as the Doppler effect. The Doppler effect, the easiest way to remember it is with sound. Okay. So how do we know that the universe is ever expanding? So we know about the Doppler effect. We know about cosmic radiation. So let's talk about the Doppler effect. Okay. And I want you to, at the same time, remember at the beginning of this unit, I did waves with you and frequency. And the reason I did that is not only because of the reference table doesn't have frequency, but also for you to figure out this right here. Okay. How many of you guys have ever been standing around 188th after school, over at Cordova, right? Or at Starbucks, whichever is your thing, right? And all of a sudden, an ambulance is coming towards you.
Me.
Okay, Owen. So, how did you know it was coming towards you? And you didn't see the ambulance yet, right?
Because I have ears and I heard the siren of the ambulance behind me.
Right, because as the ambulance is coming towards you, its frequency, right? The wave frequency is a lot, right? That means that the wavelength is smaller and it's closer together, okay? As it was moving away from you, even if you couldn't see the ambulance, you can still tell it's moving away from you. The reason for that is because its frequency is less, which means its wavelength is longer. So when it's coming towards you, you have short waves, which we know can penetrate more, right? Versus the long wave frequencies that can penetrate less. Let's see if it'll work. No, didn't want to work. Okay, so I had like a little noise, but it didn't work. All right. Okay. Well, the same thing happened here. This whole Doppler effect, of course, neither one of my links want to work. The Doppler effect is exactly that. That's when, as it's coming closer to you, it gets louder and louder and louder until it passes you, and then it gets less and less and less. Okay? So, how to put this into words? So, it's when an object is moving relative to the observer. So, the object would be the ambulance, and you are the observer. So, when it is coming towards you, all right, when it comes towards you, right, it's going to be shorter waves at a higher frequency. Okay, so it's shorter waves at a higher frequency, which makes it, if you're looking here, right, it's a higher frequency. It's at a higher it's higher than 300 hertz. And you guys know what hertz are because when we did wavelengths, we talked about them, right? They're just a unit for sound and for waves in general. Okay, that's all you need to know about them. So when it's coming towards you at a higher frequency. Okay. In 1929, Hubble actually observed something very similar to this when we had this light that was being emitted from the stars. Okay, that electromagnetic radiation. Remember I told you that would be really cool if we were in school, but we're not right now. And I showed you the different lights, how it was the fingerprint, that every element gives off a different amount of wavelength of light at a different colors, right? That whole Roy G. Biv thing. You guys remember me doing that with you?
Yes.
Okay. So that light that gets emitted from the stars, we can see it through that either a telescope, which then gets broken down into what's known as that bright line spectra, that emission spectra, right? And we can see what type of elements make up each of the stars. Well, what Hubble discovered was that over the years, those wavelengths had shifted. Okay, so if let's say this was hydrogen, let's just say this was hydrogen's different wavelengths, right? Over the years, those wavelengths stayed exactly the same distance apart, but they shifted a little. Notice all I did was move it slightly. Okay, so that evidence, okay, is all part of the Doppler effect, right? It's not just sound. Now we're talking about light. Okay, so what Hubble discovered is that emission spectra was no longer in the exact same part it was years later. Okay, so when light moves away from something, its wavelength is expanded or it gets longer. It means it shifts to the red side. Now I would highlight that. Okay, I would absolutely highlight it, do what you got to do. Okay, this is what's known as a red shift. Okay, so if you see, compared to its original emission spectra, if the spectra shifts to the red end, so if those lines all of a sudden just go to the red side, that's what's known as red shift. That means it's getting further and further away from you. You guys okay so far?
Yeah.
Okay. It's just the opposite if it's shifting toward you. So if you're shifting away, it moves towards the red. If it's shifting towards you, it moves to the blue end of the spectrum. Okay. What happens is that wavelength is squeezed together. So that's the above 300 hertz when the ambulance is coming towards you. Okay. The wavelength is shorter, which means you're going to have more of a frequency, which means that noise is going to get louder. The same thing happens here. Okay. When the wavelength is shorter, you're going to go towards the blue end of the spectrum. Okay. The way you're going to remember this is blue to you, red spread. Okay. So if it shifts to the blue, it's moving towards you. If it shifts to the red, it's spreading away. So blue to you, red spread. Blue to you, red spread. Okay. Now, just because it's completely towards the blue end of the spectrum does not mean that it has moved towards you. You have to compare it to the spectrum from years before. Okay. So this one's not as good of a picture. I don't like it as much.
Miss Gonzalez,
What's up?
could you go back just for like a couple of seconds?
This one?
Yeah, thank you.
Excuse me. Let me know.
Thank you, Undone.
You good? Okay. All right. So this is what it would look like. I don't like this picture as much. I'm actually going to get rid of it. All right. So here, the one in the middle is the original unshifted spectra. Let's just say it's from 50 years ago of one specific star. Okay. You see how the lines are in all three of them. They're exactly the same distance away from each other. It doesn't matter if we shifted to the blue or we shifted to the red, right? There's still the same amount of lines. I would, guys, if you can, take a picture of this, put this in your notes, and then get ready. I'm going to be talking about it. So I'll give you guys a second to do that. Okay, so like I was saying before, all three spectra here have the same number of lines. The lines are the same thickness and distance apart from each other, no matter which way we shift it. Okay, that's very important because they will give you a known spectra and then ask you to identify whether it's moving towards you or moving away from you. And some of them will have maybe thinner lines or thicker lines. They'll be closer together or further apart from each other. So you really need to understand that each one of these lines does not change. It's just, did they shift towards the blue end of the spectrum or towards the red end of the spectrum? So the number of lines does not change. The thickness does not change. The distance between each of the lines does not change. That's very important. Okay. So how do I know this one on top is blue shifted? Well, let's look. It took the whole spectrum and shifted it to the blue end. Notice I'm saying blue end and not left, because sometimes they will switch it and blue will be on the right side. So you have to say to yourself, if it's at the blue end of the spectrum where it just shifted to that side, okay, it means it's moving towards you. Okay, whereas this bottom one here is shifted to the red end of the spectrum and therefore it's moving away from us. They have proven that galaxies have been, they're shifting to the red end of the spectrum and therefore they are moving away from us. This is how they're proving that the universe is still expanding outwards. Okay. Okay, like we were just saying. Right? So as the star, it becomes more compressed, right? We have more frequent. If the star is moving away from us, the wavelength gets longer, and therefore the frequency is less, and it shifts to the red end of the spectrum. Okay? All right, so let's look at this, right? Here we have the original spectrum. Is this moving towards the red end or the blue end of the spectrum?
The red end.
So then, therefore, this is which kind of shift?
A redshift.
And is it moving towards us or away from us?
Away from us.
Exactly. Do you guys all see that? I
Yeah.
love how they did this also, guys. They drew arrows from the one that they know to the one that they don't know, and then you can actually physically see it moving towards the red side. You're welcome to do that as well. It's not required, but it is a little trick that can help you. Okay. Okay, so let's watch the Doppler video. Commercial.
The RPG mobile hit of 20.
The Doppler Effect. In Sheldon's words,
It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
the Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it, they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency. And if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of the road. That's you, and a car drives past you very fast. As it does so, it honks its horn because you're standing in the middle of the road.
Because who does
The honk
that?
to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even if it's a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does that mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves mean a redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang and an indication that the Earth might get very lonely in the distant future. Thanks for watching this video. Let me know if you got something out of it. Bye.
All right, ladies and gentlemen. So that is the end of the period and pretty much the end of this unit completely. All right. Yeah, that's it. So you guys have a good day. That's the end of astronomy. Tomorrow I won't see you guys, but again, I will post for you the what we're doing and everything else. All right, guys. So